Thank you for the invitation to speak. I'm Richard and I'm at Manchester. I'm going to talk about quasimorphisms and diffeomorphism groups. This is joint work with Jonathan Bowden at Regensburg and Sebastian Hensel at Munich. So throughout the talk, M will be a smooth manifold. Typically it will be closed, so it'll be compact and without boundary. We're interested in the diffeomorphism group, which consists of the orientation preserving compactly supported diffeomorphisms from M to M. This group has a natural topology associated with it, which has connected components. Diff node of M will be the component containing the identity. And today we're interested in the algebra of diff node of S, where S is a surface. I'd also like to stress that the results and techniques of this talk also apply equally to the homeomorphism groups. So our techniques apply to both settings. But we'll just write diff throughout for brevity. Now the main theme of this talk is to import techniques from the mapping class groups and get them working for the study of diff node of a surface. Now these two groups appear on opposite ends of a short exact sequence that defines the mapping class group. So you might guess that these two groups have in some ways the opposite behavior. And in most cases, I suppose that's true. So for a start, the mapping class group is a countable group. It's finitely generated by Dane twists, as was shown by Dane and Nikorish. But it has uncountably many normal subgroups. This can be seen by using geometric group theory. So the mapping class group acts on the curve graph, which was introduced by the late Bill Harvey. Mazur and Minsky showed that the curve graph is hyperbolic. The action is co-compact, but the action is far from proper because vertex stabilizers are infinite. Nonetheless, Sebastian and Fujiwara showed that the action satisfies weak proper discontinuity. Damani Giordano's used this to show that the mapping class group is SQ universal, which means that any countable group embeds in some quotient group of the mapping class group. In particular, it has uncountably many quotients, and so it has uncountably many normal subgroups. Relatively speaking, the algebra and geometry of the mapping class group is well understood. And there are many stories about the algebra and geometry of the mapping class group, which I can't go into here due to time. But many of these results on the algebra and geometry stem from the groundbreaking work of Mazur and Minsky in the geometry of the mapping class group and the geometry of the curve graphs. On the other hand, diff node of S is an uncountable group, yet it only has two normal subgroups. It's a simple group, which can be understood from the work of Martha Thurston and David Epstein. In terms of its algebra and geometry, diff node of S is much more mysterious. So for example, it's been understood for some time now that in the mapping class group there are no higher rank lattices. This is known as the Farb-Kleimanovich-Mazur theorem. On the other hand, for the diffeomorphism groups, this is known as Zimmer's conjecture. This seems to be wide open for the case of the homeomorphism group of S. So that's the algebra. It's much harder to understand. What about the geometry? Well, only recently, Katie Mann and Christian Rosendahl showed that there's a well-defined quasi-isometry type for these groups. Not a great deal is known for their algebra and geometry. So one point of the talk is to introduce some new tools to study the diffeomorphism group of a surface, which comes from the mapping class group. So we're going to introduce a curve graph, which we call C dagger. It turns out to be infinite diameter and hyperbolic, and diff node acts on it by isometries. And so we're able to import some techniques from geometric group theory and mapping class groups to study these groups. So what about an application of this? Well, we'll get to that, but first we need to introduce some background so we understand the statement of our theorem. So I'd like to define the fragmentation one. So I need to define, first of all, what a disk-supported map is. A map is disk-supported if its support lies in some open disk in your manifold. It turns out that the disk-supported maps generate diff-naught of your manifold. In other words, for all f, there's some finitely many disk-supported maps, so that the product of these maps equals f. Whenever we get a generating set for a group, we then get a word length function. When the generating set is the disk-supported maps, the word length is equal to the fragmentation norm. So the fragmentation norm of f is just the minimal n such that f is a product of n disk-supported maps. And the fragmentation norm of the identity is defined to be 0. Now this gives us some sort of metric on our group, which measures how far from the identity you are in terms of disk-supported maps. Now the fragmentation norm is quite difficult to compute. There are some easy observations that we can make. We understand when it's 0, we understand when it's 1, when it's at least 2. But it's quite difficult to say more than that. Difficult to say when it's exactly 4, for example, or indeed computing it in general. Here's a basic example. Take an open annulus. I'd like to define a point push around the core curve. So imagine putting your finger down on the surface and dragging the surface along the core curve once. And you get this picture on the right-hand side. Let's call that map f. Now do f to the n. And we can ask what the fragmentation norm of f to the n is. That's a function in terms of n. Is that function linear? Or does it grow sublinearly in n? Or is it a bounded function? I'm going to tell you the answer later, but do have a think about it. Another norm that we can define on these groups is the commutator length norm. So Mather and Thurston showed that diff-naught of m is perfect. So every element is a product of finitely many commutators. Turns out that the homeomorphism groups are also perfect. And an argument of David Epstein then shows that both these groups are simple as well. So we can also consider the commutator length norm on these groups, which is basically the number of commutators required to write down an element. So we get a natural question. We have this commutator length function on our group. When is it a bounded function? Well, it's bounded if there's some a priori bound on the number of commutators required to write any element as a product of those commutators. Well, if this function is bounded, then we say that the group is uniformly perfect because the number of commutators required is uniform. Turns out that for many examples of manifolds, these norms are bounded. So in a highly influential paper of Burago, Ivanov, and Polterovich, they show the following manifolds satisfy this. So if we take any open M-ball, or an open annulus, or in general, any portable manifold, for example, an open handle-body. If you'd like to know what a portable manifold is, I recommend looking at that paper. It's really well written. It's a joy to read. What about closed manifolds? Well, you can take any n-sphere, or any closed orientable free manifold. Then whenever M is one of these manifolds, the fragmentation norm is bounded, and the commutator length norm is bounded. So diff-naught of M is uniformly perfect. And indeed, this is true for any conjugation invariant norm in these groups. So the fragmentation norm of f to the n of our point push earlier on the open annulus is uniformly bounded. And this is totally not obvious. So the fragmentation norm is quite mysterious, but it is in fact natural in an algebraic sense. So these conjugation invariant norms, these can be algebraically defined. So it's an algebraic notion for a group. But it turns out that for any conjugation invariant norm of diff-naught, there's always some constant c such that rho of f is at most c times frag f. So this algebraically defined thing turns out to be coarsely bounded from above by this topologically defined thing. That's a really nice corollary from the previous theorem. How do we prove it? Well, you just write the map F as some product of finitely many disk-supported maps. And then what we can do is we can conjugate the Fi so that their supports lie in a fixed open ball of our manifold. And then by the previous theorem, we see that rho of Fi is N of C. By conjugation invariance, we're allowed to conjugate the Fi, and the value of rho won't change. And then by the triangle inequality, we see that rho F is then at most C times N, where N was the fragmentation on the depth. So we're done. But of course, all of this will be almost tautological if all conjugation invariant norms were bounded for all diff naught of M. So natural question is there a smooth manifold out there where the fragmentation norm is unbounded on diff naught of M? Well, it turns out if you take an orientable closed smooth manifold of dimension at least 5, it's a theorem of Tsuboi that diff naught of M is uniformly perfect and frag is bounded. In dimension 4, Tsuboi needs that the manifold has a handle-body decomposition without two handles. So after we know all these theorems, we're left with dimensions 2 and 4. For closed orientable smooth manifolds, we're left with closed surfaces S with positive genus and full manifolds with two handles. So the main theorem of our talk today states that whenever you have a closed surface of positive genus, then there is an element with positive stable commutator length in the group diff naught of S. In particular, diff naught is not uniformly perfect, and the fragmentation norm is therefore unbounded. These are the first examples of closed smooth manifolds M, where diff naught of M has unbounded fragmentation norm. And again, I'll just say that this theorem also applies to the homeomorphism groups. If you don't assume closed, you just want an example of some manifold where diff naught of M is not uniformly perfect, then the annulus with boundary was already known to have diff naught of M uniformly perfect, which is a theorem of Emmanuel Milliton. So how do we prove this theorem? The main tool is quasimorphisms. So we need a quasimorphism to provide a positive SCL element. And then we get that the commutator length is unbounded, and so the fragmentation is unbounded. These quasimorphisms are going to come from an action of diff naught on the hyperbolic graph C dagger. So let's just say what a quasimorphism is. A map from your group to the real line is a quasimorphism if it's almost a homomorphism. In other words, this term here is uniformly bounded, depending only on the map, on the elements. Notice that for a homomorphism, this term should be 0. Okay? If you have an unbounded quasimorphism, then that means that some element has positive SCL somewhere. Why is that true? Well, observe that phi of the identity is bounded, and phi of any commutator is also bounded. By the way, this is just an elementary exercise from the definition. Now notice that if phi is unbounded, then there must be some g such that phi of g to the n is linear in n. So you could take g such that phi of g is like 10d or something like that. And then phi of g to the n would be linear in n. And then notice that such a g will have positive SCL. Because if you try to write down g to the n with commutators, then you'll need linearly many, because the commutators get sent to something bounded. And so we get a positive SCL element, and so g can't be uniformly perfect. Now there's a converse to this called Bavard duality. A weak version of it states that if there's some positive SCL element, then there's an unbounded quasimorphism out there that proves this. So if you have a group where you suspect an element has positive SCL, then there should be an unbounded quasimorphism proving that. But in general, it's very hard to find such quasimorphisms. Now, there are three main sources of quasimorphisms in mathematics. You get them from dynamics, symplectic geometry, or geometric group theory. Today, we're doing very much geometric group theory, because we're acting on a hyperbolic space. Let me just remind you what hyperbolic spaces are. So we say a geodesic metric space is hyperbolic if there's some uniform constant delta only depending on the space, such that any triangle of geodesics satisfies that the delta neighborhood of 2 of the edges contains the third edge. Now, if you squint your eyes a little, then this picture on the left looks like a tree. And that's how you should think about hyperbolic spaces. They are tree-like. If you take, let's say, any 4 points in the space, then the metric on those 4 points will behave exactly like the metric in a tree up to some uniformly bounded error. Now, hyperbolicity plays an important role in mathematics. So, for example, Cantor and Lamy used an action of the Cremona group on a hyperbolic space to show that it's not simple. And also, hyperbolic groups in geometric group theory play a vital role in the solution of the virtual fibering and Parkin conjectures in free manifolds, using the work of Agel, Groves, Manning, Danny Wise, and many other people. Now, whenever you act by isometries on a hyperbolic space, there is indeed a classification for the types of isometry that you can have. Any isometry is either elliptic, parabolic, or loxodromic. Elliptics have bounded orbits. Parabolics have one fixed point infinity and have unbounded orbits. And the loxodromics, the main important ones for today, have a quasi-geodesic axis on which f acts by translation. The axis I'll denote by a sub f. You can think of it as a geodesic axis up to some bounded error. These are the most important elements today. So do please remember the notation for the axis. Right, so we're going to be using this wonderful criterion of Vespino and Fujiwara, which guarantees that your group will have unbounded quasimorphisms. So what it states is if you have this lovely action by isometries on a hyperbolic space X, such that you have two loxodromic elements f and g, such that f and g are independent, then there are in fact many unbounded quasimorphisms in the group G, which means that it has infinite dimensional second bounded cohomology. Today we just need one unbounded quasimorphism. What does independent mean? It means that once you fix axes AF and AG for f and g, it doesn't matter how you move the axis AF by some element h in your group, then HAF cannot fellow travel AG further than some uniform constant L, which depends on delta and the quality of the axes AF and AG. That's what independent means. So no matter how I move this axis by an element of my group, I can't get it to fellow travel AG more than L. So what's an example, or what's a non-example rather, of a action that doesn't satisfy the Vespino-Fujiwara condition? We can take the group PSL2R that acts by isometries on the hyperbolic plane. Now, if you take any two loxodromics in PSL2R, they have geodesic axes, but there's always an H that takes this axis to this axis, and therefore they fellow travel forever. And so any two loxodromics can't be independent, PSL2 are. But PSL2Z also acts on the hyperbolic plane, and it does satisfy the best Fino-Fujiwara condition. You can see this by using the fairy tessellation, which PSL2Z preserves, if you know what that is. Now, the reason why best Fino-Fujiwara introduced this condition was because they were interested in the mapping class group acting on the curve graph. They were able to show that any subgroup of the mapping class group is either virtually abelian or has infinite dimensional second bounded cohomology. In particular, this gives a new proof of the Farb-Kleimanovich-Mazur theorem that no higher rank lattice appears in the mapping class group. In the case of the mapping class group acting on the curve graph, it satisfies a very nice condition called weak proper discontinuity, which means that G and H are not independent if and only if G and H have positive powers that are conjugate. It's a very nice alternative definition. But our group diff naught of S cannot have a WPD action on any hyperbolic space because it's a simple group. So unfortunately, we can't use this simpler criterion to get independent loxodromics. This makes things a little bit trickier later on. So I'm ready to now define what our curve graph is. And if you know what the ordinary curve graph is, then great. It's very similar. But if you don't, here's the definition. Let's just focus on the case where genus is at least 2 for brevity. We'll define C dagger of S to be the graph where the vertices are smooth, simple closed curves on the surface, which are not null homotopic. So they don't bound a disk and they're not homotopic to a point. And they're edges between alpha and beta if and only if alpha and beta don't intersect. In the genus is 1, we allow slightly more edges to ensure that this graph is connected. This becomes a metric space when we set each edge length equal to 1. So here's an example of some vertices in C dagger. We've got this red curve here. It's adjacent to this blue curve because they're disjoint. And the blue curve is adjacent to the pink curve. But the red curve and the pink curve aren't adjacent because they intersect. Our main theorem now follows from the fact that the C dagger is hyperbolic, and the natural action of diff naught of S on C dagger satisfies the best Fino-Fujiwara condition. We can then deduce that there are unbounded quasimorphisms, and so the commutator length and the fragmentation norm are unbounded. I'd like to just say a couple of ingredients that go into the proof, just very briefly. To show that this is hyperbolic, we use the theorem of Alexander Rasmussen on the uniform hyperbolicity of a certain family of graphs. And we also use some work of Mazur and Minsky on pseudoanisolves that go into the construction of loxodromics of diff naught on C dagger here. And I'm going to end my talk now with a thought, or question rather. Is this the first example of a simple group with an action by isometries on a hyperbolic space satisfying the best Fino-Fujiwara condition? Do you know of any other such groups satisfying this? I'm not sure. So this is possibly a first. Okay, I'm going to stop the talk here. Thank you very much for listening.